Today we are going to discuss a very important phenomenon of bits, particularly which happens in case of sound wave, in case of radio waves, and also in case of laser light. Actually, in my previous video on vibration, when we have discussed the superposition of two simple harmonic vibrations or oscillations of slightly different frequencies, then I have already discussed this phenomenon of bits, and I have told you in that very lecture that this phenomenon is exhibited particularly in case of waves. So this is just a repetition. I have already discussed these things, but as vibration produces waves, particularly when you talk about sound wave, then this phenomenon becomes more prominent. So independently, now I am providing you a video on this phenomenon of bits, particularly in sound wave, and as I have told you, this is also exhibited by the radio waves and the laser light. I will also explain that this phenomenon cannot be observed if we consider two independent sources of light. Why in case of two independent sources of light this phenomenon of bits is not observed, that will be also explained in this lecture. So previously you have studied the phenomenon of interference, and in case of interference you have seen that when the two waves get two or more waves, you can say, get superposed, then at a particular time at different positions, time is fixed but positions are different. In the region of superposition, intensity of the resulting wave varies alternately and periodically. Such phenomenon is actually called interference. So you can say that interference is actually the we have discussed actually the spatial interference. But what will happen when two waves or two vibrations of nearly equal frequencies, that is the waves with frequencies which differ slightly, get superposed? Then you will see that at the same position, space is fixed, at the same position but at different times the intensity varies in a periodic manner. That is, at the same position intensity becomes maximum, and after that it becomes minimum, again it becomes maximum. Position is same but time is different. Actually such a phenomenon is called bits. So you can say that bits is nothing, this is simply the temporal interference. Here position is fixed but time varies, and in case of interference you have discussed that time was fixed but position was different. So this is the basic difference between bits formation and the phenomenon of interference. So what is this phenomenon? I have mentioned here that when you consider two sound waves whose frequencies are nearly equal but not exactly equal, you will see in the last discussion point what will happen when the two waves will have exactly same frequencies. Then you will say bits will be not produced. But if you consider the two sound waves or two radio waves or two laser light whose frequencies are nearly equal, that is slightly different, and they travel in the same direction, then in course of motion actually the waves will get superposed, and then it is seen that the intensity increases and decreases in a periodic manner at a particular position. Okay. So actually this periodic waxing and waning, when you say waxing that means increase in intensity, and when you say waning that means decrease in intensity. This periodic waxing and waning of sound at a given position, this is a very remarkable point. This is called actually bits. So you can see I have shown here the two sources. Actually this 1 and 2 represent two tuning forks, and you know tuning forks are the source of sound wave. And when these two tuning forks are vibrated by striking it by a rubber pad, then sound waves are produced. And if you consider that the first tuning fork produces a sound of frequency nu1 and the second produces a wave of frequency nu2, and this nu1 and nu2 are almost equal, not very different, and they travel in the same direction, then at any position, let us say x equal to x, they get superposed. And it is found that at this position intensity does not remain constant, but it varies in a periodic manner. After a regular interval of time, intensity at this point P becomes maximum and minimum. Okay. This phenomenon of variation of intensity in a periodic manner, this is called actually bits. Okay. And the number of maxima or the number of minima produced per second is called bits frequency. You will see later on how we can calculate this bits frequency. This is the basic theory. Now, prominently this phenomenon is observed in case of sound wave, but as I have told you that this phenomenon may take place in case of the radio waves and also in case of laser light. But as in sound can also in light bits of two sources of nearly equal frequencies be observed. I have written a question here. It means the question says, as you observe the phenomenon of bits in case of sound wave, in the similar manner, can you also observe the phenomenon of bits in case of light waves if there are two independent sources of light waves which produces light of nearly equal frequencies? Then can you observe the phenomenon of bits? Answer is no. In fact, the bits is observed only when the phase difference between the sources should change regularly and slowly. If there are such two sources which produces wave in such a manner that the phase difference between the waves produced by the two sources vary with time in a regular manner and its variation is very slow, only then bits can be observed. But what actually happens in case of light wave? As you know that emission of light from atoms is a random and rapid phenomenon. Okay? And the phase difference at a given point due to two independent light sources will change rapidly and randomly, not slowly and regularly. Okay? And when the phase difference will change rapidly and randomly, then what will happen? Then actually instead of observing bits, we shall get uniform intensity. And what will be that uniform intensity? That will be actually the average value of the maximum and the minimum intensity. It means I average, which will be equal to I max plus I minimum divided by 2, that will be simply equal to I1 plus I2, where I1 is the intensity of the first wave at that position and I2 is the intensity of the second wave. So we will observe actually a constant intensity, not a intensity which varies in a periodic manner. When it will happen? It will happen when you take the two sources of light which are called independent sources or ordinary sources. Just like two electric bulbs. If you consider this is one electric bulb, this is the another electric bulb, and light emitted by them are of nearly equal frequencies and they get superposed at this position P. But if the sources are ordinary light like electric bulb, then bits will be not observed, because in this case the phase difference between the waves produced by these two sources sorry will vary rapidly and randomly. Okay, and therefore at this point of interference the average intensity will be observed, not the waxing and waning of intensity. Okay, and you know I max is equal to what? You have studied in case of interference that I max is equal to I1 plus I2 plus 2 root over I1 into I2. Okay, and I minimum is what? This I minimum is equal to I1 plus I2 minus 2 root over I1 times I2. So when you will take average of these two values, you can see you will get I1 plus I2. So in nutshell, you can say that the phenomenon of bits cannot be observed in case of two independent light sources. And what is the reason? The reason is that if the sources of light are independent, that is ordinary source, then the phase difference between the waves produced by the two sources will vary rapidly and irregularly or randomly. Okay, but for the formation of bits it is necessary and sufficient condition that this phase difference must vary regularly and slowly. That's why we cannot observe the phenomenon of bits at a given point in case of the two independent sources of light. Okay, but if you consider the light sources are of laser light, okay, then you know actually the laser source are a strictly coherent source. So if you take the two laser sources of nearly equal frequencies, then the light produced by those sources will be coherent, and therefore the phenomenon of bits will be observed. Okay, in the similar manner we can also observe the phenomenon of bits if we take radio waves. Okay, in case of radio waves the phenomenon of bits is observed, and actually in that case that phenomenon is known as modulation. Actually when you talk about radio communication, and you will study in your course on electronics a chapter communication where we study the different type of modulation process, and there you will find that actually the radio waves when gets superposed, then there is an alternate variation of resulting intensity, and that is called modulation or bits. Okay, so bits is observed in case of, particularly in case of sound wave, this is most prominent, also in case of laser light and in radio waves. Okay, but in case of ordinary light this bits phenomenon is not observed. So what is this bit? I think now you have understand. This is simply the alternate variation, periodic variation of intensity at a given position. Mark it, bits will occur at a particular point. The intensity here does not vary with position. At the same position intensity varies with time. That phenomenon is called bits. So I have told you that bits is actually interference of wave, but what type of interference? This is actually the temporal interference, not spatial. Here space is fixed, position is fixed. Okay, so this is what we call the phenomenon of bits. Now we will explain this phenomenon in an analytical manner or in a mathematical manner. Okay, particularly in this discussion I am considering two sound waves, okay, of frequencies omega 1 and omega 2, and as you know bits will be only observed when omega 1 is almost equal to omega 2, that is, these frequencies differ from each other by a little amount. Okay? And let us consider that these two waves are propagating simultaneously in same direction, and we consider this direction as x direction. Okay? Now, the amplitude of both of the waves may be different. But here our prime aim is to discuss the phenomenon of bits for which amplitude will not play a very vital role. If you will take different amplitude for the two waves, you can discuss the phenomenon of bits. If you take the equal amplitude of two waves, then same phenomenon can be explained. So for the simplicity of calculation, we consider that the amplitudes of the two waves are equal. Actually, when you will take the amplitudes of two waves equal, your calculation will become easy. Okay, and the phenomenon will be well explained. So we consider that the two waves which are propagating in same direction are of equal amplitude. Now, as I have told you earlier and provided a separate video on it, displacement wave versus pressure wave, we have seen that the sound wave has actually two representation: displacement representation and pressure representation. You have already learned. In case of the displacement representation, we consider that the sound wave, which is particularly in fluid, which is a compressional wave, we can write the equation of sound wave in terms of the displacement suffered by the particles of the medium. Okay, that is called displacement representation. And at the same time, during the rarefaction and compression, pressure of the medium gets changed. So the excess pressure can also be taken as a wave function to describe the sound wave. And you have seen actually the pressure representation of sound wave is more superior, more advantageous. Okay, that's why here I have written the equation of the two sound waves in terms of excess pressure instead of the displacement. But in several textbooks, you will see that this phenomenon has been explained by considering the sound wave as a displacement wave. That is also right. Taking sound wave as a displacement wave, you can explain the same phenomenon very easily. But I have here considered the pressure representation of the sound wave. And you know, if we consider that there is a sound wave traveling in x direction and the excess pressure developed in the medium at any position x and at time t is P1, then P1 is given as P naught times sine of omega 1t times k1x. Here P naught is the amplitude of the wave and omega 1 represents the angular frequency of the first sound wave, and k1 is its wave number, okay, or wave vector you can say. And the second wave is represented by the equation P2 equal to P naught times sine of omega 2t minus k2x. Here, as I have considered that the amplitude of both waves are equal, so I have written P naught as amplitude in both cases. But their frequencies are not equal, they are slightly different. So the frequency of the second wave is taken here omega 2. Now in the same medium, if frequency of the two waves will be different, then their wavelengths will be also different because speed in same medium will be same, and that's why this k is also different, because k you know depends on wavelength. This is 2 pi over lambda. So the value of this k will be different. So these two equations represent the two sound waves traveling in positive x direction. Now in course of motion, these two waves will get superposed. And our aim is to find the resultant amplitude or resultant intensity after superposition of these two waves at a particular position. So we should talk about a situation where x has a particular value. Since position is fixed, we have to discuss the superposition at a particular point. So for simplicity, what will be the simplest value of x? If you take x equal to 0, your equation will become simplest. You cannot take x equal to 0, you can take any other constant value of x. But if x should be taken as constant, then when we will consider x equal to 0, our calculation will be most easier. Therefore, now I am considering the superposition of these two sound waves at a particular position x equal to 0. Okay. Now, you know from the principle of superposition that if at x equal to 0, these two waves get superposed, then at this position x equal to 0, the resulting in pressure or excess pressure P will be what? According to principle of superposition, this will be P1 plus P2 at x equal to 0. Okay. But what will be P1 and P2 when x is 0? You can see these two equations. If you will take x equal to 0, P1 will be P naught sine omega 1t and P2 will be P naught sine omega 2t. So after summing, you can take this P naught as a common factor, and this will be P naught times sine omega 1t plus sine omega 2t. Here, these equations also represent the two sound wave, but at x equal to 0. Now this sum sine omega 1t plus sine omega 2t can be simplified by using the trigonometric formula for sine c plus sine d. You know, sine c plus sine d, that is 2 sine c plus d by 2 into cos c minus d by 2 or cos d minus c by 2, because cos minus theta is equal to cos theta. So I have written here, this is 2 P naught is at is sine omega 1 plus omega 2 times t divided by 2, and cos either omega 1 minus omega 2 into t or omega 2 minus omega 1 into t. So I have not written omega 1 minus omega 2 or omega 2 minus omega 1, but I have written omega 1 difference omega 2. When you say difference, that means what will be larger, we will subtract the smaller from that. If omega 1 is larger, then we will subtract omega 2 from omega 1. If omega 2 is larger, then we will subtract omega 1 from omega 2. So I have written here the sign of difference. This wavy line actually represents the sign of difference. Okay. Now let us consider that this omega 1 plus omega 2 divided by 2 is equal to omega AV. Here the subscript AV represents for the average value. You can see this omega 1 plus omega 2 divided by 2 is what? This is the arithmetic mean, this is the average value of omega 1 and omega 2. Okay. And we also consider that this omega 1 minus omega 2 or omega 2 minus omega 1 or omega 1 difference omega 2 divided by 2, we assume that this is omega A. Actually this is called modulation frequency. You have already learned this in case of a superposition of two simple harmonic vibrations of slightly different frequencies. Okay. So now let us substitute omega AV instead of this and omega A instead of this. So this equation now becomes P equal to 2P naught times sine omega average into T cos omega A into T. Okay. Actually this equation 1 which we have obtained, this equation represents the resultant wave after the superposition of two sound waves at position x equal to 0. X equal to 0. Okay. This is the equation of resultant wave. So you can see that actually this equation is does not represent now a progressive wave, but this is just like a harmonic wave, or you can say this is just like a standing wave. Okay. Now actually here this 2p naught times cosine of omega at is replaced by this a. A is equal to this much. I have assumed it. In fact, this a, which is equal to 2p naught times cosine of omega a into t, this is called the amplitude of the resultant wave. This is the amplitude. Okay. So this equation 2, that is p equal to a times sine omega ab into t, this is the this equation also represents the equation of the resultant wave. Okay. So the resultant wave has a frequency which is average of the individual superposing waves. Okay. And its amplitude a, you can see this is not constant, but it is an oscillatory function because here cos omega at is present. So the amplitude of the resultant wave is not constant, but it varies in a periodic manner due to this cosine factor. And you know, intensity is directly proportional to a square of the amplitude. A square of the amplitude. So if amplitude will vary in periodic manner, so definitely intensity will also vary in periodic manner. And that variation of intensity in periodic manner at a given position, which we have assumed here x equal to 0, that is called the phenomenon of bits. So you can see with time t, resultant amplitude will vary in periodic manner, and that's why according to this relation, resultant intensity at a given position will also vary in a periodic fashion with time. And that variation of intensity with time in a periodic manner is called bits. So at the same position x equal to 0, intensity will alternately change. It will increase and after some time it will decrease. Okay. It will become maximum and after some time it will become minimum at the same position. Position is not different. And that's waxing and waning of intensity at a given position is called bits. Okay. And the number of maxima or number of minima produced per second is called bits frequency. And the minimum time interval after which intensity becomes maximum or the minimum time, you can say, between the two successive maximum or two successive minimum is called period of the bits, and the reciprocal of that period of bits will be the measure of bits frequency. So now you can find what will be the bits frequency, how you can obtain it. Okay. So now after getting this this equation of resultant wave, now we are going to discuss the important facts regarding this bits. Okay. First of all, as I have told you that you can see the resultant amplitude A is equal to 2p naught cosine of omega a into t. Sorry, omega a into t. Okay. And the resultant intensity I is equal to a times sine of omega average into t. So you can see that the resultant wave is a harmonic wave, as I have told you, and its frequency is equal to omega AV, and omega AV is actually the average of omega 1 and omega 2. Omega 1 and omega 2. Okay. This is the average of these two frequencies, and its amplitude is A. But this amplitude, you can see, is not constant, but it varies in a periodic manner, and its value will vary between 2p naught and 0. as I have shown in this figure, the variation of A, that is the amplitude of the resultant wave in against of time. You can see this curve. At t equal to 0, the amplitude is 2p naught. Okay, and again at a time 2 pi by omega A, its amplitude becomes 2p naught. So this time interval is actually equal to its time period after which the wave gets repeated. Okay, so from here you can see that the maximum value of the magnitude or the modulus of maximum value of amplitude is 2p naught, and the modulus of minimum value of amplitude is 0. So the amplitude varies in a periodic manner. Its maximum value is 2p naught and its minimum value is 0. Okay. When you take the amplitude of the two waves equal, then minimum amplitude is 0. But if you will take that the amplitudes of the two waves are not equal, they are actually p naught to 1 and p naught 2. Actually in that condition you will see that the maximum value of amplitude, that will be equal to p naught 1 plus p naught 2. Okay, and the minimum value of amplitude, mod of A minimum, that will be equal to p naught 1 a difference p naught 2. Okay, but if p naught 1 and p naught 2 are equal, then that will be equal to 0. Okay, so the amplitude of resultant wave is not constant, but it varies in periodic manner with time between these two limits, 2p naught and 0. Okay, now let us see. As I have told you earlier, that the intensity is directly proportional to the square of the amplitude. So when A will be maximum, then I will be maximum, and when A will be minimum, then I will be minimum. Okay, and as I, you can see, is equal to A times sine omega A, A is equal to 2p naught cos omega at. Okay, cos omega at. So A square will be 4p naught square cos square omega at. But 4p naught square is a constant factor. So A square will be maximum or minimum, that will be decided by cos square omega at. So when cos square omega at is maximum, then intensity will be maximum, and when it is minimum, then intensity will be minimum. So now let us discuss the maximum and minimum value of intensity separately. First of all, we are going to discuss when the maximum intensity will occur. And you know, for maximum intensity, this cos square omega at must be equal to maximum. And you know, maximum value of cos square theta is equal to what? That is plus 1. So for maximum intensity, this cos square omega at must be equal to 1. And if cos square omega at is plus 1, then what will be cos omega at? You know, this will be plus minus 1. And therefore, the general value of omega A into t will be equal to n pi, where n is 0, 1, 2, 3 and so on. Actually, you can see, when you will take n equal to 0, then omega at t will be 0. And you know, cos 0 is plus 1. When you will take n equal to 1, then omega A into t will be pi, and cos pi is minus 1. When you will take n equal to 2, cos omega at will be cos 2 pi, that will be plus 1. So alternately, you can see this omega at will be equal to what? 0, pi, 2 pi, okay, and 3 pi, and in alternate manner you can see at 0 it will be plus 1, at pi it will be minus 1, at 2 pi it is plus 1, at 3 pi it is minus 1. Okay, so this is the general value. But you have seen, we have assumed that this omega A is equal to omega 1 difference omega 2 divided by 2. So this much will be equal to n pi. Okay. But if you are not talking in terms of the regular frequency, that you consider that nu1 and nu2 are the regular frequency or the frequency of waves measured in hertz, then this angular frequency omega 1 is given by 2 pi nu1 and omega 2 is given by 2 pi nu2. So instead of omega 1 and omega 2, now you can write 2 pi nu1 and 2 pi nu2. So your result becomes 2 pi times nu1 difference nu2 times t divided by 2 equal to n pi. Okay. Now this pi and pi will cancel, this 2 and 2 will cancel, and therefore for n equal to n, the time t is now written as tn. T has been replaced by tn. This actually indicates that when n is equal to n, then we denote the time by the symbol tn. So Tn will be equal to n divided by nu1 difference nu2. In fact, what this time Tn represents? This is actually the time when the intensity nth maxima will be observed. Here n actually represents the order of maxima. What number of maxima? When the intensity will become maximum at nth time, then that time is represented by Tn. Okay. So from this general result, you can now find all those times at which intensity will be minimum at the position x equal to 0. Remember, I have considered position fixed, and that fixed position is x equal to 0. So at what are those times at which intensity at x equal to 0 will be maximum? Now you can easily find by taking the different value of n. So let us now first of all put n equal to 0. So the time t0 when maxima will occur, that is equal to 0 from that relation. Then n will be 1, so that time will be t1 and that will be 1 over nu1 difference nu2. n equal to 2, time will be t2 and that will be 2 over nu1 difference nu2. So the first maxima occurs at 0 time, second maxima occurs at time t1, third maxima occurs at time t2 and so on. So what will be actually the interval of time between two successive maxima? So you can see the time interval between the first and the second maxima, that will be equal to t1 minus t0, and the time interval between the second and the third maxima, that will be t2 minus t1, and in general the time interval between the nth and n minus 1th maxima, that will be tn minus 1. But from the above values, you can see when you will find t1 minus t0, t2 minus t1, at tn minus 1, always you will get 1 over nu1 difference nu2. So you can say that the time interval between any two successive maxima is equal to 1 over nu1 difference nu2. That is reciprocal of the difference of frequencies of the two waves. Actually, as I have told you earlier, that the time interval between two successive maxima, that is called the period of bits. So actually this TB, which I have represented, this 1 over nu1 difference nu2 has been represented by the symbol TB. Actually this is the bits period. I have not mentioned it here. I will mention it later on. But this TB is what? This is time interval between any two successive or any two consecutive maxima. Okay, that may be first and second maxima, that may be 10th and 11th maxima, that may be 25th and 26th maxima, but time interval will be same, and that time interval is constant, and that is equal to 1 over nu1 difference nu2, and this is actually called bits period. Okay, so I think you have clearly understand this calculation. Now let us see to find all those times when intensity will be minimum, and for that you have to take the minimum value of this function cos square omega a into t, and the minimum value of cos square omega a t is 0. Okay, and if cos square omega a t is 0, cos omega a t will be also 0. So what will be the general value of omega a into t? The general value of omega a into t will be 2n plus 1 into pi by 2. That is the odd multiple of pi by 2, where n will be again 0, 1, 2, 3 and so on. You can also take that this may be 2n minus 1 into pi by 2, because you also know that 2n minus 1 is also an odd number. But in this case, when you take 2n minus 1 into pi by 2, then you have to take n equal to 1, 2, 3 and so on, not 0. When you will take n equal to 0 in this result, and when you will take n equal to 1 in this result, value will be same, that will be pi by 2. Okay, so you can equivalently take 2n minus 1 into pi by 2, only then you should think that n cannot be 0, but we will have to start the value of n from 1, not from 0. Okay, so I have taken here plus, so you can find the result by taking this plus sign. Now again omega a, this is omega 1 difference omega 2 divided by 2. Okay, so this is the result. Now again omega 1 and omega 2 can be expressed in terms of the regular frequency measured in Hertz, that is nu1 and nu2. So this will be 2 pi nu1 difference nu2 times t divided by 2 equal to this much. Now this pi, this 2 will cancel. Okay, and therefore for n equal to n, Tn will be equal to 2n plus 1 divided by 2 times of nu1 difference nu2. So this equation 6 actually measures all those times at which resulting intensity will be minimum at the position x equal to 0. At the same point, these are the times at x equal to 0 when intensity is maximum. But this equation will give you all those times when at the same position x equal to 0, the resulting intensity will be minimum. Okay, and that all those times can be found by taking the different values of n here. So see this result and find the different time. When you will take n equal to 0, you will get the time t0, that will be 1 over 2 times nu1 difference nu2. Okay, when you will take n equal to 1, then you will get t1, and that will be 3 upon 2 times of nu1 difference nu2. For n equal to 2, you will get t2, that will be 5 upon 2 times nu1 difference, and in this way you can find t3, t4, t5 and so on. Again, if your aim is to find the time interval between the two successive minima, how you will find? The time interval between the first minimum and the second minimum will be t1 minus t0, and the time interval between the second minimum and the third minimum, that will be t2 minus t1, and similarly time interval between the nth and n minus 1th minimum, that will be tn minus tn minus 1. And again, when you will put the values from here, you will see that this is equal to 1 over nu1 difference nu2. So the time interval between two successive minimum, any two successive minimum is 1 over nu 1 difference nu 2. And you have also seen that the time interval between two successive maximum is also 1 over nu 1 difference nu 2. So this is also called beat period, and this is denoted by the symbol TB. So what do we have obtained here? You can see actually the time interval between two successive maximum or the time interval between two successive minimum at the same position is constant, and that is equal to 1 over nu 1 difference nu 2. And as I have told you that this time is called period of the beat or beat period. Okay. And you know, frequency is just reciprocal of the time period. So if beat period TB is equal to 1 over nu 1 difference nu 2, then beat frequency. What is beat frequency? Beat frequency means number of bits produced per second, or number of maximum produced per second, or number of minimum produced per second. How many maxima is produced in 1 second? How many minima is produced in 1 second at a particular position? That is called bits frequency. And that bit frequency, if you denote it by the symbol nu b, that will be 1 over TB. And since TB is 1 over nu 1 difference nu 2, so 1 over TB will be simply nu 1 difference nu 2. This is a very important result. So actually the beat frequency is equal to the difference of the frequencies of the superposing waves. For example, if you consider, if you take two tuning forks, the first tuning fork produces a sound of frequency, let us say 400 Hz, okay, and the second tuning fork produces a wave, sound wave of frequency 405 Hz. Then what will be the bits frequency? This will be actually 5 Hz, okay, 5 Hz. You have to take 405 minus 400, difference you have to take. It means in that case, in 1 second, intensity will become maximum 5 times, and intensity will also become minimum 5 times. It means, so the beat frequency in that condition will be 5 Hz. Okay. So remember it, this is very important result for objective question, that beat frequency is simply equal to the difference of the frequencies of the two superposing waves. And here you can see, if nu 1 is exactly equal to nu 2, what will happen? Then beat frequency will be equal to 0. So no beat will be produced if you will take two sound waves whose frequencies are exactly equal. So in the definition in the beginning, I have told you that for formation of bits, you have to take two sound waves of slightly different frequency, not exactly equal. Because if the frequencies of the two waves will be exactly equal, no bits will be produced. Actually, I will explain this fact in last point of my discussion again. You will see. Now, we are going to see a very important fact. I have written, when bits are produced but not heard. Bits will be produced, बीट पैदा होगा लेकिन सुना नहीं जा सकता है, ऐसा कब होगा? Now we are actually going to see this fact or explain this fact. As you have seen that in case of bits formation, as I have told you, that actually bits is the phenomenon of interference. But what type of interference? This is actually the temporal interference, not spatial. At a particular point, at a given point, intensity is not constant. In case of interference, you have seen that if here there is maxima, then always it at this point there is maxima, and if here is minima, that intensity is minimum, then permanently intensity is minimum here in case of interference. But what happens in this case? In this case, if at this position at some time intensity is maximum, after some time intensity becomes minimum at the same position, such phenomenon is called bits. Okay. So in this case you can say that interference is not sustained. Okay. We cannot observe the sustained interference. Now, have you an idea about the persistence of human ear? Actually, the persistence of human ear is about 1/10 second. What does it mean? When you say that human ear has persistence of hearing which is 1/10 second or 0.1 second, what does it mean? It means if on the human ear two sound signals will be incident in an interval less than 0.1 second, then the ear cannot distinguish between them. Okay, ear cannot distinguish. Ear will feel that a continuous sound wave is falling on it. Okay. But if the time interval between two successive sound pulse incidencing on the ear is greater than 0.1 second, then ear is able to distinguish them. That is called persistence of hearing. So now let us consider that if bits frequency is greater than 10 Hz, then actually the ear will be not able to detect them. It will detect the maxima and minima only when per second the number of bits produced will be less than 10 Hz. So I have mentioned it here that bits will be detected by the ear only if bit frequency is less than 10 Hz. Only then your ear will be able to detect the bit. The ear or any the ear which is a detector here. So what is the persistence of hearing of the detector? That decides actually the bits will be observed or not. Bits will be produced, but the detector is able to detect them or not. That depends on the persistence of hearing. For human ear, since the persistence of hearing is 1/10 second, so if in 1/10 second one beat will be produced, then it will distinguish it. But if more than one beat will be produced in 1/10 second, then it will not detect it. That's why we simply say that if beat frequency is less than 10 Hz, then bits will be produced and it will be also detected by our ear. It means we will hear the bits. But if now consider that the bits is producing and bit frequency is greater than 10. For example, per second 20 bits are produced. Per second 15 bits are produced. Per second 100 bits are produced. The bits are producing, but our ear will be unable to detect it. Okay. So if the bits frequency is greater than 10, then the bits will be produced, but no beat will be heard by our ear. So this is a very remarkable fact. Bits are produced, but we can't hear it. We can't detect it. Okay. When it will happen? It will happen when the number of bits produced per second is greater than 10, then we will not hear the bits. It does not mean that bits is not producing. Bit पैदा हो रहा है लेकिन हम सुन नहीं रहे हैं क्योंकि वह 10 से ज़्यादा हो रहा है. लेकिन अगर 10 से कम बीट पैदा होगा तो वैसी स्थिति में बीट पैदा भी हो रहा है और हम सुन भी रहे हैं. ठीक है. So this is a remarkable fact. You can hear the beat only when bit's frequency is less than 10, but you can't hear the beat when the bit frequency is greater than 10. Actually, what happens in that condition? When the bit frequency is greater than 10, actually in that condition our ear observe the continuous sound intensity. It does not feel that intensity is varying. It feels an average intensity which is constant. And that average intensity you have seen is given by I max plus I minimum divided by 2, which you know is equal to I1 plus I2. So in this condition, the ear does not feel that there is a waxing and waning of sound, but it hears a continuous sound, a sound of constant intensity. So what I have told you, the beat is produced and it is heard. बीट पैदा होता है और इसको सुना जाता है कब? When beat frequency is less than 10. And if beat frequency is greater than 10, then bits is produced. Bits is fastly produced, but our ear is unable to hear it. So the ear feels that no beat is producing. Okay, so this is a very remarkable fact. And why this 10? Because the persistence of hearing of human ear is 1 by 10 seconds. Although the persistence of hearing for different detector will be different. I am talking about only the human ear. If there is an electronic detector, then the persistence of hearing may be different. Okay, the persistence of hearing for the dog will be different. Okay, so mark this important fact. This is very important for your objective type question. Now finally, I have told you that when nu1 is equal to nu2 or omega 1 is equal to omega 2, then you have seen that bit frequency will be 0, and I have told you that in that condition no bits will be produced. Now I am explaining actually that fact. See here, when omega 1 is equal to omega 2 and you consider that this is omega, then we have seen that omega A, which is equal to omega A1 difference omega 2 divided by 2. Since you are now assuming that omega 1 is equal to omega 2, so omega A will be 0. And omega average, this will be omega plus omega divided by 2, which will be equal to omega. So the omega average will be omega. In that condition, you can see our result for P was what? That was 2P naught cos omega A into T times sine omega average into T. Okay, but now omega A is 0, so cos 0 will be 1 and omega average omega. So the equation for the resulting wave will be 2P naught sine omega t minus kx. Okay, so you can see I have not taken here x equal to 0. When you will take x equal to 0, the resulting wave will be simply 2P naught sine omega t. So you can see this is just equation of a progressive wave, not of a standing wave. Okay, so this is a progressive or traveling wave with frequency omega and amplitude 2P naught. Its amplitude is not varying, but it is constant. In the previous situation, you have seen that the amplitude of the resultant wave was A, which was varying with time, because this was equal to 2P naught cos omega A t. But now this resultant amplitude is simply 2P naught, which is constant, and therefore intensity will be proportional to or equal to 4P naught square, 2P naught whole square. And if P naught is the amplitude of each wave, P naught square will be the measure of intensity of each wave. So resultant intensity will be 4I naught. I naught is here equal to P naught square. And therefore you can say that the resultant intensity now is constant, not variable. It does not vary periodically with time. And if there is not a periodic variation of time, it means no bits is producing. Because bits means what? This is just the periodic variation of intensity at a given position. So in this case, when we consider the superposition of two waves of exactly equal frequency, then intensity at a given position does not vary periodically. It remains constant at that point, and so no bits is produced. Okay. So now I think this fact is now very clear to you. So for bits formation, frequency should be different. But if you will take a large difference, see here, when bits will be observed, only when the bits frequency will be 10. So if you now consider that nu1 is equal to 400 hertz, okay, and nu2 is equal to 420 hertz, then what will be the bits frequency nu b? This will be 20 hertz. The bits are producing, but can you hurt this beat? Answer is no. You can't hurt it. You can hurt the beat only when bit frequency is less than 10 hertz. That's why in the definition of bit it is said that there should be two waves of slightly different frequency. If the frequency of the two waves will differ by a large amount, then you can't hear the beat. Therefore, in definition, it is said that the frequencies should be nearly equal but not exactly equal. When frequencies will be exactly equal, you can't hear the beat, bits is not produced. And when frequencies differ by a large amount, by greater than 10 hertz, then bits are produced, but we can't observe it. The human ear can't observe it. So in the definition it is said that bits will be produced only when the two sound waves are of nearly equal frequency, that is, the waves should have a difference of frequency equal to or less than 10 hertz. Then only the observable bit will produce. Okay. So you must take two sound sources which do not produce waves of equal frequency, which do not produce waves of very unequal frequency, but they produce waves of almost equal frequency. Okay. Actually, this fact, when you say that bit is producing, now let us consider there are two sound sources. This is your source number 1 and this is your source number 2. And this source 2 is a standard source. When you say a standard source, it means it produces sound of a particular frequency which is known. Let us say that it produces a frequency nu naught. This is fixed. This is called a standard source. You know that this source will produce a frequency of nu naught. And this is a source which frequency can be changed. Okay. Now let us sound this source S1, and when bit will be produced, what does it mean? It means the frequency produced by S1 is different from the frequency produced by S2 from the standard source. Now let us change the frequency of the wave produced by this source S1. If bit frequency is increasing and your aim is to match the frequency of the wave produced by S1 to the frequency produced by the standard source, then you have to decrease the frequency, and the frequency of the wave is decreased until bit frequency vanishes. And when bit frequency will vanish, it means now the frequency of the wave produced by source S1 and that by the standard source become equal. Actually, this principle is used by musicians in tuning their instruments. When you say tuning their instruments, it means the musician actually match the frequency of his musical instrument with a standard source. And for this, they sound their instruments against a standard source and tune it until bits disappear. That is, sound of uniform intensity is heard. When bit will disappear, it means the intensity produced by the musical instrument and that of the standard source become equal. Okay. So in this situation, the frequency of their instrument is equal to that of the standard source. So this principle of bits is utilized by the musician to tune his musical instrument with a standard source. Okay. So I think clearly you have understand these concepts. Okay. Now actually finally I have shown the variation of the excess pressure P with time t in this graph. How pressure varies with t, actually you have seen that this P is equal to 2p naught cos omega a into t times sine omega average into t. So this P also varies with, this is just a equation of a standing wave, and what will be the envelope, what will be the wave pattern of variation of P against of T, I have shown here. Okay. So this is all about the bits, and I have actually dealt this concept separately in case of waves here, but you have also seen this concept in the superposition of two simple harmonic vibrations. So after these two lectures on bits, your idea about the bits is will have become very clear, and I hope. Okay, thank you very much.